Hi, let us begin the statistics of paramagnetism using the canonical ensemble theory, and we had already done in our previous video the classical approach. Now we are trying to deal with the quantum mechanical approach. So if we want to deal with the quantum mechanical approach, then we need to assume the corresponding magnetic moment for in quantum mechanical formalism, which is nothing but G mu B J, where G is the paramagnetic ratio, mu B is the Bohr magneton. So G is 3 by 2 plus S into S plus 1 minus L into L plus 1 divided by 2 of J into J plus 1. As you all know, S is the spin quantum number, L is the orbital angular momentum quantum number, J is the total angular momentum quantum number, G the paramagnetic ratio, and mu B is the Bohr magneton, which is given by E H cross by twice n. Bohr magneton, it's an universal constant. Okay, so let us try to find the corresponding. So the energy would be the potential energy of such a dipole in the presence of external field is equal to minus of mu dot B, which is equal to minus of G mu B J dot B in the external magnetic field. Let's say the external magnetic field is along this, and this is J. So if the angle is theta, then we can write this as minus of G mu B J cos theta B, which is equal to, what is J cos theta? This is equal to M, the magnetic quantum number B. Okay. Now we can define the partition function in the statistics, which is Q1 beta single particle partition function, to be equal to e to the power minus of beta E, okay, which is equal to summation over I. So this is going to give us e to the power minus of beta G mu B B M, and M runs from minus J to plus J. Remember, we have certain orientations to space quantization, so M can take values from minus J to plus J in quantum mechanics. So we want to calculate the corresponding partition function. From here we can assume, let's say we assume that for beta G mu B B into J to be equal to X, we intentionally assume this beta. Okay, so we can write the partition function Q1 beta to be equal to e to the power of X. So this would give us X by J to be equal to beta mu B G B. Okay, B is the magnetic field, external magnetic field. So e to the power X by J M, and M running from minus J to plus J. So we can say that this is basically a geometric series with the first term as e to the power minus x by j minus of x. This is a GP with first term e to the power minus x, because for n is equal to minus j this would become, and common ratio is e to the power minus of j plus 1, so this would become e to the power of x by j minus j plus 1, okay, divided by e to the power of minus x. So sorry, e to the power of minus x. So this is going to give us x by j. So common ratio is e to the power of x by j, because this is the common ratio CR. So for such term, the sum of the geometric series give us e to the power minus x into e to the power of how many terms total? Twice j plus 1. So twice j plus 1 into x by j minus 1 divided by e to the power of x by j minus 1. A into b to the power, if a be the first term and b be the common ratio, then a into b to the power n minus 1 by b minus 1. So that is the value of the partition function. We can just slightly modify this so as to get a known form. We can write it as e to the power minus x, which is there, and then we take common 2j plus 1 of x by 2j common, such that this becomes e to the power twice j plus 1 x by 2j minus e to the power minus of 2j plus 1 x by 2j, okay, and in the denominator also we take e to the power x by 2j common, such that in the denominator we are left with x by 2j minus of x by 2j. So we can see that this x by 2j cancels with this part, and this also cancels with this part. So we are left with 2 sine hyperbolic 2j plus 1 x by 2j and sine of hyperbolic 1 by 2j into x. So this is our partition function, one particle partition function. We can further do this for the n particles simply by taking a power of n for n particle. So our n particle partition function Qn can be written as sine hyperbolic 2j plus 1 by 2jx divided by sine hyperbolic 1 by 2j into x whole to the power n, because we know that for n distinguishable particles, here these are the dipoles which are localized, and that's why they are distinguishable. So for that the n particle wave function, and immediately we can write the corresponding Helmholtz free energy. A to be equal to minus kT ln Qn which is basically equal to minus of nkt ln of sine hyperbolic 2j plus 1 by 2j into x minus ln of sine hyperbolic 1 by 2j into x sine hyperbolic. Okay. Now, if we know the Helmholtz free energy, then we can easily calculate the corresponding magnetization M, which is equal to minus of del A by del B at constant nt. So, if you want to, but this is in x, so del from here we can write del B to be equal to beta mu b g j del x. So del b can be written as beta mu and there is minus sign, so this would become plus of n k t beta g mu b j, and del b can be written as del x of the whole thing ln of sine hyperbolic 2j plus 1 by 2j into x minus ln of sine hyperbolic 1 by 2j into x. So this kt and beta cancels out because beta is, so we are left with magnetization to be equal to n g mu b j, and this is going to give us sine hyperbolic is going to give us cot hyperbolic 2j plus 1 by 2j into x, and with a factor, there should be a factor here, 2j plus 1 by 2j, okay, and minus of again 1 by 2j and cot hyperbolic 1 by 2j into x. This function, we call this as Renewal Function bx, and we can write this as ng mu b j bx. We can again plot the Renewal Function where bx is equal to 2j plus 1 by 2j cot of hyperbolic 2j plus 1 by 2j into x minus 1 by 2j cot of hyperbolic 1 by 2j into x. We can plot Renewal Function bx versus x for different value 2, 4, 6, 8, and if this is 1, then for bjx, call it bj of x for different values of x, for different values of field and temperature, you can plot it, and for j is equal to half, it goes something like 2, 4, 6, 8 and so on. It goes something like this. This is for j is equal to half. J is equal to 3 by 2. It goes like this. J is equal to 10,000. It goes like this. And for j tending to infinity, Renewal function actually converges to the Lagrange's function, Langevin function, Langevin's function. And again, if we want to consider the two cases, the first case is the low temperature and high magnetic field case, then we can get that expression, and that would be 1. So two cases for low temperature, high magnetic field, that is x is much greater than 1. In that case, Bjx would tend to 1 and the magnetization would be equal to Ng mu Bj, where this is the quantum mechanical magnetic moment for the high temperature low field. X is much less than 1. In that case, Bj is equal to x by 3 into 1 plus 1 by j. And if that be the case, then the corresponding we can just derive the value. We can just put it over here. For case B, M would be equal to Ng mu Bj, and Bj is replaced by x by 3 into 1 plus 1 by j. Okay. Now what is x? X is beta mu Bgj, so we can write it as Ng mu Bj, okay, into beta mu Bgj b whole by 3, and this is going to give us j plus 1 by j. So 1j cancels out and we are left with Ng mu b whole square, okay, j into j plus 1, okay, and beta is 1 by kt, so thrice kt b. And this is something which is the quantum mechanical expression for the magnetization. You can realize that this is mu square, the magnetic moment square quantum mechanically, and one can define the corresponding susceptibility also from here, del m by del b, which is equal to n of g mu b j into j plus 1 by thrice kt, which is equal to c by t. Again the Curie's law for paramagnetism. So that completes more or less the paramagnetism statistics in terms of canonical formalism.